Hi, so we'll be learning about paging in OS today. So first of all, let's understand about main memory and process. So as you can see, our all programs are stored in hard drive, which is disk. Okay, so here your programs are stored, your applications. Okay, but whenever you run the program by double clicking on it, then your application opens up. Okay, but when you click a program, then that program uh, comes in main memory. Okay, so this is your main memory, which is random access memory. So for example, there is a program P1, then then the set of instructions that the program P1 was formed of will come in the main memory. Okay, so main memory is also has some size. So for example, main memory is of 400 MBs. So P1 will come here. Okay, so P1, let's say it is of 200 MB. So P1 comes here, and now there is more programs that are in the disk. They will also come. So for example, now again now let's say 50 MB program comes P2, and now let's say another program 200 MB P3. Okay, now now there is another program P4. Okay, so now first of all, before the P4 comes in, you actually closes the program 50. Okay, you closes the program 50 MB. So now this program leaves the memory. So this leaves the memory, and now this is empty. So now how your main memory looks like. So here your P1 is sitting 200 MB and P2 is gone. So this 50 MB is free. This is available, and now 200 MB uh, uh, is taken by P3. Okay, so now this 50 MB and this 50 MB is present. Okay, this is available. This is your main memory. Now P4, which is of 100 MB, is sitting in your disk, and you opens that program, but that program uh, cannot be bring into the main memory. Why? Because the main memory has does not have a space of 100 MBs. So you can see the P4 will as a whole program needs 400 MBs of memory, but you can see that the main memory has 50 MB here and 50 MB here. So it has a total of 100 MB memory, but it is splitted. Okay, it is fragmented. So therefore P4 program cannot be open. Okay, so this is what we call as P4 demands 100 MB, and in your main memory you have 100 MB, but it is splitted. So this is what we call, this is a problem that we call internal fragmentation. Okay, internal fragmentation. So therefore, to solve this problem, a concept called paging is introduced. So now let me un- uh, tell you about paging. So in paging, your main memory, okay, your main memory is divided into uh, fixed fixed size of partitions. Okay, into fixed size of partitions. For example, if this is your main memory, okay, and let's say this is of 300 MBs. So now let's say this is 50 MB. So your one partition size is 50 MB. So partition size is 50 MB. So this way 50, 50 and so on. So how many partitions you will have? 300 divided by 50 is 6 partitions. You will have 6 partitions. So now as you can see in the above problem here, there was no partition earlier. Okay, there was no partition here. Okay, whenever a program needs to be open, the whole program of its size, for example 200 MB will take up the available space of 200 MB in the main memory. But now here the main memory is divided into fixed partitions. Okay, so now if a program is now let's say a program P1 is of 200 MBs. Now 200 MB program cannot be put here in one partition because 200 is greater than 50. So you cannot put the bigger program into a smaller space. So therefore you have to divide your program also. Okay. So now the since as main memory is divided into fixed size of partitions, your process is also divided. Your process is also divided into same size of partitions. Okay, same size of partitions. So now say as your P1 is of 200 MB, so you can see here your P1 is of 200 MB, so it will be divided into four partitions. This is of 50 MB and this is of 50 MB. This is also and this is also 50 MB. So your this partition can now sit in any one of the partitions here. For example, this is your 50 MB partition in the main memory. So this is, let's say, this is the partition uh, 0 P0. This is partition 1 P1 P2 P3. So let's say P0 sits here, P1 sits here, P2 sits here, and somewhere along, somewhere here, P4, P3 sits here. Okay, so this way now your different partitions of program process sits in different partitions of main memory. Okay, so now before we understand this, so now the partitions in main memory. So now the partitions in main memory are called frames. Okay, this is called a frame. This is your main memory and this is your process. In process, it is called a page. Okay, it is called a page. So in process, the partition is called page, and in main memory, the partition is called frame. So now here, let me first of all tell you like how this is distributed. So main memory size, first of all, see here, this is your one location. Okay, in main memory, this is your one location, and this location has a address. So address is 0000. Okay, and similarly another location, this is your another location, it has address this 0001. So to give you a very brief idea of what how does that work, so for example here is your CPU. Now CPU wants the content which is stored here in location 000. Okay, so there are various uh, wires that are going from CPU to main memory. Okay, so now you can see there are 4 bits that are actually needed to know the location in your main memory. So if you want the content of any location in the main memory, so for example, if you want the content of here, so you need this address. Okay, 0110. So from CPU, four different wires are gone, and each wire will carry the location. So for example, if you want 0110, then 0110. So your CPU will send these bits to the main memory, and main memory will send the content which is stored at this location back to the CPU. So this is how it works. So now let's come back to our OS topic. So yeah, so this is your frame, and this is your, so as you can see, so this is generally a byte addressable memory. Okay, this is byte addressable memory. What does that mean? That your each location, okay, this is your one location. So your one location stores 1 byte. So here you can see at most 1 byte data. So one one byte means 8 bits. Okay, that means 8 zeros, ones. So 1 2 3 4 5 6 7 8. So this is your content now. This is your content. let's say 10111001. Okay, this is your content stored at memory location 00. So at memory location 0000, what is the content stored? Content is 10111001. Okay, so uh, so now, yeah, so now what is a frame? So frame is a fixed partition in which your main memory is divided. So as you can see here, uh, a frame, this is a frame. So this is a frame. A frame has two memory locations. How many memory locations? Two. And one memory location stores 1 byte. One memory location stores 1 byte. So a frame. So here a frame size is what? 2 bytes. Okay, because it is storing two memory locations. And as I have already told you above, that main memory and process both are divided into same size of partitions. So the page size and the frame size will be same. So it is 2 bytes. So it is also 2 bytes. So 1 byte is contributed by this and 1 byte is contributed by this location. So a page size will also be 2 bytes. Okay. So now here you can see from the above example, the process size is what? So here you can see how many logical addresses do we have. So logical address is the process address. So there are 1, 2, 3, 4, 5, 6, 7, 8. So that means 8 and each stores 1 byte. That means the total process size is 8 bytes. Okay. And what is the page size? Page size is, as you can see here, 2 bytes. Okay. So now how many pages are in the process? Number of pages in the process, you can see 8 bytes divided by 2 bytes. It is 4. So you can see here, this is your one page, this is second, this is third, and this is fourth. Okay. And similarly, you can see here, let me show you. So this is your main memory size. So what is your main memory size? So you can see here there are how many addresses in the memory? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 bytes. Okay, 16 bytes is the main memory size. And the frame size is what? Frame size is also 2 bytes. So now we have to know how many frames are in the main memory. So you can see here that this is your one frame, this is your second, third, fourth, fifth, five, six, seven, eight. How many frames? 8 frames. So you can see here main memory size divided by frame size. So it gives us 16 by 2, which is 8 frames. So you have 8 frames. So now let's see about page table. So this is your CPU. So CPU knows the address of process. Okay, which instruction it wants. So whatever. So what is stored here? Here. So for the process, uh, these are the instructions. Okay, here you can say 1 byte of instruction is stored. Okay, 1 byte of instruction, and then second byte is stored here, third byte is stored here, fourth byte is stored here. So CPU needs to execute those instructions, so it knows the address of process. Okay, so let's say CPU knows that it wants 010, whatever is written here, it wants. So but this whole, so where this address is a part of, this address is a part of page 2. Okay, this address is a part of page 2. So so now where is this process stored? So as I already told you, the programs are bring in the main memory and are stored in main memory. So this whole process is stored in in this main memory. Okay. So for example, let me uh, this is page 0, this is page 1, page, so let me, sorry, page 1, page 2, page 3, page 4. So now these pages are stored in this main memory location here. So let's say page 1 is stored here, let's say page 2 is stored here, page 3 is stored here, and page 4 is stored here. So now there is a page table. Okay, there is a page table. So page table stores which page is stored in which frame. Okay, so here is the page number and here is the frame number. So this is a mapping. Page table is a mapping. So you can see here page 1, page 2, page, there are how many pages? There are page 1, page 2, page 3, and page 4. So now where are these pages stored? Page 1 is stored in frame. So this is your first frame, this is second. So it's stored in second frame. So frame number second. And similarly page 2 is stored. So 1, 2, 3, 4. So this is frame 4. And this is frame 6. This is frame. So 1, 2, 3, 4, 5, 6, 7, 8. This is frame 7. So this is frame 4, frame 6, frame 7. Okay. So now see, CPU knows the address of process. Okay, so for example, CPU has already executed these two instructions 000 001. Now it wants the instruction which is stored at 010. Okay, but this 010 is the logical address. Okay, this is not exactly where the instruction is stored. Instruction is stored in your main memory. Okay, so and the main memory's address is different. As I already told you, there are the four wires that are going in, so each carrying a bit of the location of the main memory. This is called physical address. Okay, but CPU knows only the address of process. So now it refers the page table. So now CPU knows 010. It wants 010, that is page 2. So it will refer page 2 from here. Where it is stored? It is stored in frame 4. So now here it is frame 4, where it is frame 4 here, and its address is 0110. Okay, so this is how the mapping is done between page number and frame number. So here the actual frame numbers are stored. So let me show you that also. So so you can see here how many pages are there. There are 4 pages. So page 1, let me show you here. So 1, 2, 3. Okay, this is your process, and these are multiple pages. So this is your page 1. So 00, page 2, 10, page 3, 11, page 4. Okay, so this is how actually you uh, assign the counting in a binary format. Okay, and similarly for the main memory, you have 8 pages. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So for 8, how many bits you required? You need to do log 2, which is 3. Okay, so 000 001 10 011 100 101 110 111. So this is now your frame numbers. Okay, this is your frame number, and this is your page number. So now you can see from the page table, page 1 is, so page 1 is 00, then 01 10 11. So now 00 is, so now page 1 is stored in frame 2. So what is the frame two's address? This is 001. Okay, 001. So and from from page 2 is frame 4. So this is frame 1, frame 2, frame 3, frame 4. Frame 4 is 0, 1, 1. And frame 5, frame 6, frame 7, frame 8. So 6 and 7, 1, 0, 1. And frame 7 is 1, 1, 0. So now let's iterate again. What does CPU want? CPU wants the instruction that is stored at which location of the process? 0, 1, 0. Okay, it wants 0, 1, 0. Then from page table, so this is your page table. From page table, so 0, 1, 0. Okay, so 0, 1, 0 is stored in which page? So 0, 1, 0 is stored in page 2. So page 2 is 0, 1. From here it will get the frame number 0, 1, 1. So now frame 0, 1, 1 stores the instruction. Okay, so now frame 0, 1, 1, where it is 0, 1, 1. So from here you can see this is your 0, 1, 1 frame. Okay, so now it will simply get the address from so 0. So what the CPU wanted? CPU wanted 0, 1, 0. This is your process instruction number. And what is the page table? What is the page number? Sorry, page number. So page number was 0, 1. What is your frame number? Frame number is 0, 1, 1. So now what is the actual physical address where your instruction is stored? It is 0, 1, 1, 0. So you can see there is a relation here. So from logical address, the prefix is your page number, okay, and rest is what we call byte offset. So you can see here CPU gives us the logical address which is 0, 1, 0. So 0, 1, 0. So page number is 0, 1. From here I get to know what is page number 0, 1. And then using it from page table, I got the frame number. What is the frame number for 0, 1? It is 0, 1, 1. So this is my frame number. So I will pick frame number from here, 0, 1, 1. And what is the byte offset? 0. I will took byte offset and put here. This forms my physical address. This forms my physical address where the actual instruction is stored. So now 0, 1, 1, 0. Okay, as you can see here. 0. So 0, 1, 1, 0 is this one. So I want this particular instruction. So you can see the CPU requested this one and I got it from here. I got this actual physical address. So this is how paging works.